For this lab, the objective was to create a drag racer using the given motor and gearbox that can move as fast as possible through a cardboard tube track. In addition to maximizing speed, we were challenged to try and increase the angle of the track and overall minimize the time score for the car to travel through the tube. One of the central concepts to this lab was the characterization of the motor. The rotations per minute, or RPM, at each gear ratio was measured, while the stall torque, or the torque load needed to stop output rotational motion, was measured for the small two gear ratios to prevent stripping of gears. Once this data was taken, we used MATLAB to calculate a function or motor characterization curve relating RPM and stall torque for each gear ratio.
We started out by drawing a free body diagram of the forces acting on the car and the tube, and summing the forces in the x and y directions. Since the acceleration phase is so short, we assumed the car was moving at a constant velocity and that the force equation summed to zero. This allowed us to find an equation for the minimum torque needed to move the car. Since speed and torque are inversely related, this helped us pick the fastest gear ratio that would satisfy the car's torque requirements. Using the equation relating torque and speed for the gear ratio selected, we also solved for our car's expected time and velocity by plugging in the torque the car required. Since a lot of groups doing this lab previously had issues with cars flipping in the tube, we also used the FBD to find an equation for the net moment. This is important because if the net moment is not clockwise, the car will flip backwards. We wanted a clockwise moment that pushed the car into the tube so it did not flip. While designing our car, we put all the equations into a MATLAB script so we could see how different parameters would affect the car. One of the most important design factors is the size of the wheels, but this parameter is significantly constrained by the size and curvature of the tube. Therefore, we started by choosing a wheel radius of 2.5 centimeters, since this was about the average of what other groups said worked for them, and decided to focus on manipulating other parameters to optimize our design. The mass of the car is another important consideration, because a lighter car requires less torque and therefore will move faster. For this reason, we made most of our components out of MDF. We also prioritize the car's center of gravity as a design parameter. If the car's CG creates a positive moment, it will flip backwards in the tube, which means game over. To design a car with a proper CG, we use a trial and error process. We designed the car in SolidWorks with each component set to the proper material density so we could find the position of the CG. Then we plugged the dimensions into the moment equation in MATLAB to see if it worked. We adjusted things until the MATLAB script said the car would not flip. We found it helpful to move the battery pack as far forward as we could, since this is the heaviest part of the car and affects the CG the most.
While fabricating the car mostly out of laser-cut MDF, there were several adaptations that were made and obstacles that we worked around. Superglue and hot glue were both utilized to secure the battery pack, motor, and the axle supports on the car. Hot glue was used to create spacers that secured the front wheel and prevented it from sliding on the front axle. Rubber bands were also used to attach the battery pack and motor to the body of the car, in addition to lining the wheels to add friction. However, since no thick rubber bands were available, multiple thin ones were cut, lined up side by side, and glued to the front wheel. There were concerns that this was not precise and would decrease the roundness of the front wheel, impeding motion. For the back wheels, originally rubber bands were placed around the wheels but were not secure when testing and slid off. During our initial test, the car failed to travel up the 15-degree incline. We speculated that this was because the rubber bands were not in contact with the tube on the back wheels and did not have enough friction. After the rubber bands were glued, the car was able to travel successfully up the incline of the tube as predicted. Overall, our raw time is 4.84 seconds, and when adjusted for the 15-degree incline of the track, this time score was 3.84 seconds. This deviated from the expected raw time of 1.11 seconds significantly. Some of the hypothesized reasons for this deviation included the fact that the battery pack did slightly hang off the back of our car and the imperfect use of rubber bands to add friction. An improved design may work to change the center of mass by staggering the battery pack and gearbox and altering the wheel diameter.